Full OpenMP functions are for setting the number of threads, for instance from a command line argument, and to measure the execution time. So we print the difference between these. We can specify the scheduling, meaning how the iterations in a for loop should be distributed to different threads. And static scheduling gives approximately the same number of iterations to each thread. That's the intent, but if it's not evenly divided, then it may not be the same. This has the least overhead, but can cause load imbalance. And another way is to use dynamic scheduling, and then you can think of it as there is a work queue, and each thread goes and gets size number, this size here, of iterations and works on them, then goes back and takes another size number of iterations. If we don't specify the size is 1. It's important that these are contiguous. And the reason why that is important is for cache performance, as we will see later. Well, it's spatial locality, and also a reduced number of coherence misses, as we will come to. There is a slight difference between, alternative to dynamic scheduling, and that is to take into account the number of not yet scheduled iterations, so the number of remaining iterations. When a thread wants to get the number of a certain number of iterations, it can ask for that, but it will get at least this number of iterations, except for at the end. But the scheduler checks how many iterations remain and how many threads are working, and then it distributes it fairly, taking this into account. Okay, and we can use the environment variable OMP schedule, and it should be static, dynamic, or guided, but we cannot set the size in that case. So, for example, if we want to do matrix multiplication, we can do it like this, and we say that all of this should be private, and we use static scheduling, and the size should be, well, this n divided by the number of threads that we use. Okay, so num prox is basically the number of threads. Well, it is the number of threads. Okay. Oops, I missed one. So, if we have some different parallel work that should be done, and then, but not in a for loop, for instance, but we have a number of sections that can be worked on concurrently. Then we can use OMP sections, and then OMP section, and a number of these, and these sections are worked on concurrently. Reduction is meant computing something from an array. So there is a loop, this loop has data dependence on the sum variable. We can specify that the I should be private, since it's a loop variable, but not the sum. It would not work. Okay, this has happened in vectorizing and parallelizing compilers for a very long time. So there is a developed technique to handle this situation, and it is to work into a private variable and compute a partial result, and then it will be summed if it's an addition after this parallel loop. So we can, and this is called a reduction. Okay, so we can specify like this. So OMP parallel and for and reduction on this operator and this variable. So then each thread will compute the partial sum, and then they will sum. Okay, so we can write all of this in one line. So basically the only thing we have to do is to insert this line, and all the details will be taken care of by the compiler and runtime system. Okay, and we can use reductions not only for addition but for this as well. And then the variable that we are working on will get a suitable start value, such as 0 for a sum or 1 for a multiplication, and all ones for AND operator. So tilde 0 produces, I mean, it is bitwise complement, so it produces as many ones as fit into an int, and that's a suitable start for a AND.